All right, right now we're going to talk about Chapter 3, Energy, Chemical Reactions, and Cellular Respiration. And we're going to start off with how living organisms require energy to power muscle, to pump blood, absorb nutrients, exchange respiratory gases, synthesize new molecules, and establish cellular ion concentrations. Now, glucose is also broken down through metabolic pathways. We'll talk more about that in a bit here. It forms ATP, the energy currency of the cells. Without ATP, there's no muscular activity, there's no muscular contraction, so no movement of the body. As far not to mention the cell dies without ATP. That said, learning objectives, you should be able to, after this section, describe the two classes of energy, describe chemical energy, one form of potential energy, and the various forms of kinetic energy, list the three important molecules within the body that function primarily in chemical energy, state the first law and second law of thermodynamics, and explain why energy conversion is always less than 100%. So energy is simply the capacity to do work. Right? There are two classes, potential and kinetic. Potential is stored energy, energy of position, and it typically referred to more. Typically, we find this a lot in chemical. We find it in chemical bonds, generally speaking, between atoms or in bonds with molecular compounds. That said, once it's in motion, once like electron is released and it's in motion, would be then kinetic energy. Kinetic energy is the energy of motion. Anything that's moving. Both can be converted from one class to the other. Okay. Now, potential energy in the plasma membrane, the concentration gradient exists across the plasma membrane, but between the inside and the outside of the cell. This keeps the extracellular fluid and the intracellular fluid separate. And if you recall from the phospholipid bilayer of a cell membrane, we have the polar heads on the outer layers, or on the walls essentially, and we have the polar tails, non-polar tails, on the inside, and we always have a higher pressure gradient on the outside the membrane or outside the cell, or in the extracellular fluid, I should say, versus the intracellular fluid, which have a lower pressure area, which is why you'll find that nutrients will often want to try to go from the high pressure to lower pressure into the cell, but they will oftentimes need assistance to get there. We'll talk more about that. Potential energy in electron shells. Electrons move from a higher to a lower energy shell, generally speaking. Kinetic energy can be harnessed to do work. Potential energy must be converted to kinetic energy before it can do work. So here we have potential energy, referring to the sodium ions that are in high concentration in the extracellular fluid outside the cell, and they're in a higher pressure area, and so consequently, they are going to try to go into the lower pressure area, which is inside the cell, and so then these sodium ions moving to an area of low concentration have kinetic energy when they are in motion. That's an example of kinetic energy there from the potential before they made that movement. And that's a concentration gradient between the high pressure to low pressure area, high pressure of the extracellular fluid outside the cell, outside the membrane, and then through that phospholipid bilayer into the cell itself is a lower pressure area in that intracellular fluid. And another example, in terms of movement of electrons, once an electron is lost, so to speak, or released, if you will, basically from the high energy shell, the valence shell of the atom, or of a compound in general, for an atom in general, really, that we have that electron now is in high energy. It's been released, energy has been released from potential to kinetic. It's in motion as it's falling, so to speak, here. And that said, that high energy state, potential is there until it's in motion. Kinetic energy is released as electrons move from high energy to low energy states. Okay. So chemical energy, it's one form of potential energy. And energy is stored in molecules' chemical bonds. It's released when bonds are broken. It's used for movement, with like ATP, molecular synthesis in many different forms, and establishing concentration gradients, like we talked about just a moment ago with the wall separating between the intracellular and the extracellular fluid outside the cell. It's present in all chemical bonds, molecules that function in chemical energy storage, triglycerides. Those triglycerides are stored in the adipose tissue or fat cells. Glucose, which is stored as a polymer in the liver and muscles, as a glycogen. And ATP, which is stored in the muscle cell, and it has a very limited amount. ATP doesn't last more than a couple seconds. So I would say 1 to 5 seconds absolute max. You'll see variations like so many things, but 1 to 5 seconds is about right for the lifespan of ATP. Kinetic energy forms. Electrical energy is the movement of charged particles. An example being the movement of ions across the plasma membrane of a neuron. Okay, a lot of brain activity, right? Would be a great example of that too. Mechanical energy is exhibited by objects in motion due to applied force, muscle contraction for walking, for gait, for moving in general. Sound energy, molecular compression caused by a vibrating object, right? That creates sound waves causing vibration of the eardrum in the ear, something you can hear. The radiant energy is energy of electromagnetic waves. Example is visible light striking the retina so we can actually see it. We'll talk a little more about different levels of radiant energy here shortly. Heat is energy of electromagnetic waves, usually not available to do work. It's heat, so consequently it heats up anything in the general vicinity of where an energy transformation or conversion occurs, but it's generally referred to as waste in that you can't then reuse that same heat. It'll heat things up, and that's what it does. Okay, and it's measured the temperature of an object, right? The amount of heat. So the electromagnetic spectrum, showing increasing frequency in this direction, increasing wavelength this direction. Radio waves have significant wavelength, but certainly a lower frequency. And then if we move toward infrared light, the wavelength will get a little shorter, and the frequency gets a little higher. Then we have visible light here, which is between 400 to 740 nanometers. Some will say nanometers, right? And then we have beyond basically visible light, you have ultraviolet light, which has actually got an even shorter wavelength. Even shorter wavelength and increasing frequency compared to visible light, and increasing to X-rays, increasing frequency further, and then gamma rays with the highest frequency of electromagnetic energy. And of course, these levels of radiant energy on the electromagnetic spectrum have the potential, this is kind of big, if too much exposure occurs, which includes some of the tests we do to examine what's going on in the body. It's not just a matter of whether these tests are expensive, but they're potentially damaging, and we have to be very careful how often they are used with someone and how they are used. It's not just a matter of the fact they're expensive to use, which a lot of people like to say about using X-rays and other tests which use some of these electromagnetic rays on the higher end of the spectrum here, or the higher frequency area and the shorter wavelength. And it can actually mutate DNA, which is not something we're really looking to do. In a very brief way of referring to something that's quite actually complex. Now, the laws of thermodynamics, the study of energy transformations. Okay, first law of thermodynamics: energy can neither be created nor destroyed; it can only change in form, either transformed or converted. Okay, it's not going to, you can't destroy energy; it's either going to be converted in some way, or transferred or transformed in some way. The second law of thermodynamics: when energy is transformed, some energy is lost to heat. The amount of usable energy is then decreased, and moving around to warm up on a cold day, as an example, when you're going to lose some heat, even though you're actually getting some energy to be able to perform work at the same time, some's lost to heat. And that being said, with heat being produced, the great example your book gave, which was crazy, and I haven't corroborated the exact estimation they gave, but referring to the idea that gasoline in your car, you put gas in your car, wasn't this ridiculous when you heard this? Maybe you knew this already, that 25% of it is actually going to be used, 75% is lost as heat and sound, right? That's crazy how much is lost versus how much you can actually use. Of course, ATP, we'll get into that. ATP becomes ADP, so it loses an organic phosphate, so you lose quite a bit of that ATP potential, really, when you convert it to kinetic energy. That said, for what did you learn? Both the movement of sodium ions from an area of higher concentration to an area of lower concentration, and the movement of electron from a higher energy to a lower energy state are examples of the mere fact that talked about moving makes it kinetic, not potential, right? Potential is exactly that. It's in a steady state, so to speak. It's actually potential for movement, but it's not moving yet. That's kinetic, okay? Muscular contraction, an example of what form of energy, and we're basically talking about ATP. We're talking about ATP specifically with muscular contraction, okay? And it's kinetic, of course, too. Kinetic energy can neither be created nor destroyed. However, according to the first and second laws of thermodynamics, what can happen to it and what is always generated is going to be transformed, right? Converted, transferred, transformed, and of course, when that happens as well, heat is going to be created. You're going to lose some energy to get some energy every single time, right? So with section 3.2, explaining what occurs in a chemical reaction, distinguish between reactants and products, and describing the three classifications of chemical reactions, and distinguish between catabolism and anabolism, or catabolism and anabolism. And I think we're going to talk about that in the next video. I'm going to cut this off here so give you more time to digest this in smaller amounts.